Do you know about the concept of the unit circle in trigonometry? In this video, I'll explain how the unit circle connects angles with coordinates and trigonometric functions. The unit circle is a circle with a radius of 1, centered right at the origin on the Cartesian plane. Its equation is simply x squared plus y squared equals to 1. In this diagram, you can see a central angle, theta, drawn in standard position, which cuts out an arc of length s along the circle. Now, consider a point P with coordinates x, y, on the unit circle, where a line making an angle theta intercepts the circle. The distance from the origin, or the center of the circle, to point P is 1, which represents the radius of the unit circle. Next, let's draw a perpendicular line from point P down to the x-axis. This forms a right-angled triangle with the angle theta at the origin. Here, this side is the opposite side, this one is the adjacent side, and this is the hypotenuse. Alright, moving on. We know that sine theta is the opposite side divided by the hypotenuse. Now, in this right-angled triangle, the hypotenuse, which is actually the radius of the unit circle, is 1. So, if we plug that in, sine theta just becomes the length of the opposite side. In the same way, cosine theta is the adjacent side divided by the hypotenuse. And since the hypotenuse is 1, cosine theta is simply the length of the adjacent side. That means, on the unit circle, cosine theta represents the x-coordinate and sine theta represents the y-coordinate of point P. So basically, we can say point P has coordinates, cos theta, sine theta. Alright, let's take point B right here on the unit circle. Now, draw a tangent line touching the circle at point B, just a straight line that grazes the circle. Next, extend the radius from the origin out to the point on the circle that represents your angle theta. The moment that line crosses the tangent, that's our point A. And here's the cool part. The length of that segment along the tangent, from A to B, actually gives us the value of tan theta. So now, this setup actually forms another right-angled triangle, and its base is just the radius of the unit circle. Alright, quick reminder. When two triangles are similar, their sides are proportional. That means, the ratio of the corresponding sides always stays the same. Now, take a look here. Triangle AOB and triangle POQ are similar. So we can compare their sides to find what we need. That gives us this relationship, side AB over OB equals side PQ over OQ. Now let's plug in what we know. AB is tan theta, OB is 1, PQ is sine theta, and OQ is cosine theta. And when we simplify that, tan theta equals sine theta divided by cosine theta. Now, let's derive the Pythagorean identities using a right triangle inside the unit circle. Imagine a triangle POQ. If we apply the Pythagoras theorem, we get PQ squared plus OQ squared equals 1, since the hypotenuse, or radius, is 1. Next, if we replace PQ with sine theta and OQ with cosine theta, we get one of the most important trigonometric identities, sine squared theta plus cosine squared theta equals 1. Now, using this identity, we can find the other two. First, let's divide every term in this equation by sine squared theta. That gives us 1 plus cotangent squared theta equals cosecant squared theta, another key identity. Can you guess the third one? In the same way, if we divide everything by cosine squared theta, we get tangent squared theta plus 1 equals secant squared theta. So, there you go. These are the three fundamental trigonometric identities. And don't forget about the other trigonometric ratios, tangent, cotangent, secant, and cosecant. They're just as important and all connect back to the unit circle too. Have you ever stopped to think, what exactly is an angle in math? Well, in this part, we're diving right into it. We'll explore what angles really mean, how they're measured in degrees and radians, and how you can easily switch between the two. Let's jump in. To really understand angles, let's think of a clock. Imagine the center of the clock as the origin, and each hand, the hour or minute hand, as a radius of a circle. When the minute hand moves from 12 to 3, it sweeps out a quarter of the circle, that's a 90-degree angle, or pi over 2 radians. From 12 to 6, it covers half the circle, that's 180 degree, or pi radians. A full rotation, from 12 all the way back to 12, is 360 degree, which equals 2 pi radians. So, just like the hands of a clock rotate around the center, angles in trigonometry show rotation around the origin of a unit circle. An angle is basically a measure of how much a ray rotates around a fixed point. The starting position of the ray is called the initial side, and after it rotates, the new position is the terminal side. That fixed point where it rotates is the vertex. If the rotation is anti-clockwise, the angle is positive, and if it's clockwise, it's negative. An angle measures how much we rotate a line from its starting position to its final position. That's what we call the initial and terminal sides. There are different ways to measure angles. One full rotation makes one complete revolution, perfect for describing large angles, like a wheel spinning 15 revolutions per second. But most of the time, we use two common units to measure angles, degrees and radians. Let's explore what they mean next. Each degree is divided into 60 minutes, written like this, and each minute into 60 seconds, written like this. So remember, 1 degree equals 60 minutes and 1 minute equals to 60 seconds. Written like this. For example, a full revolution is 360 degrees. Let's understand what degree measure means. When a line rotates from its starting position to its final position, we call that rotation an angle. Now, if that rotation is 1/360th of a full revolution, the angle is said to measure 1 degree, written as. For example, right-angled triangle is 90 degrees, a straight line is 180 degrees, and you can even have negative angles like -30 degree when rotating in the clockwise direction. Now let's talk about another way to measure angles, called radian measure. 1 radian is the angle made at the center of a circle when the arc length is equal to the radius. So, if you draw a circle with radius 1 unit and mark an arc of 1 unit, the angle formed at the center is 1 radian. Since the total circumference of a unit circle is 2 pi, one full rotation around the circle equals 2 pi radians. That's the same as 360 degrees. In general, for any circle with radius, r, and arc length, s, the angle in radians is given by the formula, theta equals to s divided by r. This simple relationship helps us connect angles, arcs, and circles beautifully. Let's understand the relation between radian and real numbers. Imagine a unit circle with center O and a point A on the circle. The line OA is our starting side of an angle. Now, as we move along the circle, the length of the arc we cover represents the radian measure of that angle at the center. Next, draw a tangent line PAQ at point A. Let's take pointer as 0. To the right, AP represents positive real numbers, and to the left, AQ represents negative real numbers. If we wrap AP anti-clockwise around the circle and AQ clockwise, every real number corresponds to a radian measure, and vice versa. So, radians and real numbers actually represent the same thing, just in different forms. Now, let's explore the relationship between degrees and radians. A full circle makes an angle of 360 degrees, which is the same as 2 pi radians. That means pi radians equals 180 degrees. Using this relation, we can easily switch between degrees and radians. For example, 1 radian equals 180 divided by pi, which is roughly 57.3 degrees. And 1 degree equals pi divided by 180 radians, or about 0.017 radians. Here's a quick look at how some common angles compare in both degrees and radians. That's all for today. If you enjoyed this video, don't forget to like, share, and subscribe for more fun math lessons. Keep learning, keep exploring, only on XploreConcepts.